Geometry, Lesson 4.1, we're learning about angles in triangles. We're going to do something different beginning with this video. This is the vocabulary in Lesson 4.1. Please take out some paper, list these on the paper, and fill them in as you're reading your text and or watching the video. Here's also a list of the theorems and corollaries in Lesson 4.1 so that you know that you have them all recorded in your notes. So let's go on. In the triangles below, we have an acute triangle, a right triangle, and an obtuse triangle. The acute triangle has three acute angles. These are three angles that will be less than 90 degrees. You've already learned about one special case of acute triangle, and that was the equiangular triangle. The right triangle has a right angle, and it can only have one right angle. We'll talk about that later. The obtuse triangle has an obtuse angle, and it also can only have one angle. And depending on how large that angle will be the definition of the shape of that triangle. So an equiangular triangle is a special case of triangle with three equal 90-degree angles. We already know that a triangle has 180 degrees. So 180 divided by 3 would be 60 degrees each. In a right triangle, the side opposite the right angle is the hypotenuse. The other two sides are legs. So AB would be the hypotenuse, AC and BC would be legs. As a reminder, the Pythagorean theorem states that the sum of the squares of the lengths of the legs in a right triangle is equal to the square of the length of its hypotenuse. So you have the hypotenuse, which is AB, and we can see that here. We have AB squared. You have the two legs, AC and BC, and you can see them here as AC squared plus BC squared. You're probably more familiar with this formula as A squared plus B squared equals C squared. It's the same formula, just expressed in a different way. In the triangles below, we're going to learn that you can also classify triangles by their sides. So the last triangles we talked about, the acute, obtuse, and right, were classified by their angles. In this instance, we have the scalene triangle, and the scalene triangle has no congruent sides. We have the isosceles triangle, and it has two congruent sides. So you can see the congruency marks here on FG and GH. The equilateral triangle has three congruent sides, and you can see the hash marks. Now, interestingly, your equilateral and equiangular triangles are the same triangles. It's a special condition, so all of these angles will also be equal. The two congruent sides of an isosceles triangle, FG and HG, are also called legs. The third side, FH, is called the base. There are angles that are formed by the two legs. The angle formed by the two legs, angle G, is its vertex angle. The other two angles, angle F and angle H, are the base angles, and we'll learn more about these later on, but the base angles are congruent to each other. Here's our first theorem for this lesson. We have the triangle angle sum theorem. The sum of the measures of the angles of any triangle is 180 degrees. You already knew this fact, but now you have the theorem to back it up. One of the things they do for this theorem is something that we haven't done often before. They actually create an auxiliary line right here, or you can also call it auxiliary, to go ahead and set up this proof. They have given triangle ABC. They construct or draw this line DB to make angle 4 and angle 1 be congruent to each other. Because they do this, you now have a situation where you have these two lines with these two congruent angles that happen to be alternate interior angles, and that makes DB and AC parallel. Because of that, they can now go on and prove that angle 5 and angle 3 are congruent by alternate interior angles. And by using the angle addition theorem, we can state that angle 4 and angle 2 and angle 5 are 180 degrees, because this now becomes a straight line which equals 180 degrees. Therefore, because we stated that 4 was congruent to 1 and 5 to 3, we can use substitution to say that 1, 2, and 3 also equal 180. I'll be showing you the formal proof for that later on. There are some corollaries from this theorem. A corollary basically carries the theorem a little further. The acute angles of a right triangle are complementary. So when you have a right triangle, you have a situation where you have a 90-degree angle. So one of the things we can figure out is that 180 degrees minus that 90-degree angle will leave us with 90 degrees. So that means that the two acute angles, your angle A and angle B, must add up to 90. So no matter what shape your right triangle is, these two angles will be complementary or add to 90 degrees. Each angle in an equiangular triangle has a measure of 60 degrees. So this is the corollary for the theorem, and we've already stated that these three angles would be 60 degrees, or 180 divided by 3. Theorem 4.1.2. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So we have angle A right here has one hash mark, and if you note on the triangle over here, angle X has 1, angle Y has 2, and angle B has 2. So these are signs of congruency. If B is congruent to Y and A is congruent to X, then by default angle C would have to be congruent to angle Z. Example 1. Find the measure of each numbered angle. Let's take a look at this figure right here. We have two triangles. We actually have three triangles, but we have two triangles that we're going to deal with. One of them has two measurements inside. The other one only has one. I'm going to begin by solving for the measure of angle 1 because I already have the other two measures. So remember, this is 180 degrees, so 180 minus the 36 minus the 60 equals the measure of angle 1. So the measure of angle 1 would be 84 degrees. Now I can solve for the measure of angle 2 because these are supplementary angles. Angles 1 and angle 2 are supplementary. They also add to 180 degrees. So the measure of angle 2 plus the measure of angle 1 equals 180. We know that angle 1 was 84 degrees. We just solved that. So 180 minus 84 equals 96. So we now have the measure of angle 1 and the measure of angle 2, and we'll solve for the measure of angle 3. So angle 3 will be 180 degrees minus 96 from angle 2 and minus 45, minus 45, which is given in the triangle, and that will give us 39 degrees for angle 3. There's different ways that you can do this. There would be different methods. You could also solve, you could use the larger triangle to start. You have 36 degrees here, and you have 105 degrees there. You could subtract those from 180 and solve from angle 3. An exterior angle of a triangle forms a linear pair with one of the angles in the triangle. Let's take a look at this triangle. We've extended one of the sides, and by extending that side, we've created this angle right here. This is called an exterior angle. So we're talking about angle 2. The remote interior angles of an exterior angle are the two angles of the triangle that are not adjacent to the given exterior angle. So the remote interior angles, interior meaning inside, will be the two angles opposite angle 2. It will not be the angle adjacent or next to angle 2. So once again, angle 2 is an exterior angle, and its remote interior angles are number 4 and number 5. You can extend each one of these sides, and you will create a new situation with a different exterior angle and different remote interior angles. The other 5 exterior angles can be drawn by extending the sides of the triangle. Theorem 4.1.3. The measure of an exterior angle of a triangle is equal to the sum of the measures of its two remote interior angles. So we're talking about angle Y right here. Its measure equals the measure of W and X. So I've gone and I've fleshed this out. I'm uncomfortable with just saying angle Y, angle W, angle X. I like to call out the angles. If you're working on a figure that has a lot of angles, this is helpful. So angle XYZ equals angle XWY plus angle WXY. And that's another way of expressing that. Let's use this figure for a problem. Example 2. Find the value of x first, that's the variable, and the measure of angle W and the measure of angle XYZ. So we're asked to find the measure of the exterior angle and one of its remote interior angles. We have the measure of the other remote interior angle. So let's solve for x first, and I have the actual formula for the theorem written right here, and I'm going to substitute values. So the remote exterior angle was 13x minus 5 equals 5x plus 3 plus 64. If I combine like items, we end up with 8x equals 72 and x equals 9. So we've solved the first part of the problem, x equals 9. Now let's substitute it in our expressions here so that we can continue to solve. The measure of angle W equals 5 times 9, which is right there, 5x, the 9 being right here, plus 3 equals 48. And the measure of angle XYZ, the exterior angle, is 13 times 9 minus 5, which is 112. So your homework for lesson 4.1 is on pages 151 through 153. It's number 1 through 16, number 22, 25 through 27, and I've also added an extra credit problem on this video. The extra credit problem is not in your book, and it's to be solved by you showing your work, not to be solved by anyone else. To get credit for the extra credit problem, you have to complete all the other problems in your homework. Let's take a look at how to do number 13. We have a triangle here, and we have an exterior angle of 140 degrees. You're asked in the problem to find each indicated angle measure. I've gone ahead and marked which ones we need to solve for. We're solving for the measure of KIH and the measure of angle K. Well, KIH is not a remote interior angle. What it is a supplementary angle to this angle, 140 degrees. So 180 minus 140 equals 40 degrees. And if this is 40 degrees, one of the things it shows you on your diagram is that this angle is congruent to this angle. This is an isosceles triangle. So this is also 40 degrees, and we now have two angles solved. Let's solve for the third, and the measure of angle K is 180. The 40 plus 40 is 80, minus 80 degrees equals 100 degrees. I went ahead and solved number 19 for you. This was actually assigned as homework. This is the proof, formal proof of what we learned in the theorem. Complete a two-column proof of the triangle angle sum theorem. And what I basically want to do is just go over the thinking behind this theorem. Once again, they drew this line, DB, and they drew it so that angle 4 and angle 1 are congruent. So if angle 4 and angle 1 are congruent because they're alternate interior angles, this proves that DB and AC are parallel. And that's listed right here. It says congruent alternate interior angles imply parallel lines. Now we can go ahead and say that angle 5 and angle 3 are congruent because we know these are parallel lines. So we use a little bit different definition, the converse of what was in number 4. Parallel lines imply the congruency of alternate interior angles. We can now go from congruency in step 5 to equality in step 6. So the measure of angle 5 equals the measure of angle 3. We can now use the angle addition postulate to say that the measure of angle 4 plus the measure of angle 2 equals this angle, DBC. And we can now state that DBC plus angle 5 are supplementary because this is a straight line. Once we've proved that they're supplementary, we can say that they're equal to 180 degrees. And now we can state that angle 4 plus angle 2 plus angle 5 are 180 degrees. Because we already proved that angle 4 and angle 1 were congruent with angle 5 and angle 3, we can now state that the measure of angle 1, 2, and 3 equal 180 degrees by substituting for the angle 4 and the angle 5. So it's a longer theorem that we've done before, but it's actually very basic. Number 24. It says use the figure to find each measure. You won't always be solving with just a simple triangle. Sometimes you'll have different kinds of figures. It says find the measure of AEB, which was this angle in the middle of this diagram. If the measure of ABE is 78, which I've marked, and the measure of BAE is 62. Now this looks familiar. We can say 180 minus 78 minus 62 equals 140 degrees. I'm sorry, 40 degrees. Number 41 wasn't in your assignment, but this is important to know. This is actually a formula for helping to solve the angles of different figures. It says divide the polygons into triangles by drawing diagonals from one vertex to the other vertices. And we've done this before in a lesson. Let's look first at this four-sided figure. It only has one diagonal. You cannot, if you remember, cannot use the sides of the figure to draw from vertex to vertex. And we split it into one diagonal here, and we end up with two triangles. So it has a number of sides, which are 4, the number of triangles, which are 2, and the sum of the angle measures. Well, 180 plus 180 is 360. Let's look at the pentagon here. Pentagon has 5 sides. If we divide it up using diagonals, we end up with 3 triangles. 180 times 3 is 540. Let's look at a figure, a hexagon that has 6 sides. It has 1, 2, 3 diagonals, and, or should I say, 3 diagonals that create 1, 2, 3, 4 triangles. 4 times 180 is 720. The more sides you have, the more complicated this would get. So we need a formula. Let's just look at the pattern. If you have 7 sides, you'll have 5 triangles. 5 times 180 is 900. If you have 8 sides, you'll have 6 triangles. 6 times 180 is 1080. So here is our formula. If you have an unknown number of sides, the formula is n minus 2, which is the number of triangles. You can see this. The number of triangles is the sides minus 2. 5 minus 2 is 3. 6 minus 2 is 4, and so forth, times 180 degrees. So be sure to have this formula in your notes, and it's solving the sum of the angle measures in a polygon. Here's the extra credit problem. Once again, this is not in your book. You must show your work. You must do all of your other problems to be able to get credit for this problem. Be sure to contact me if you need any assistance, and have a blessed day.